Tudor Padurariu from the University of Bonn will continue his lectures on BPS cohomology and quasi-BPS categories. So please, Tudor.
Yes. Yeah. Thank you again for the introduction, and thank you for coming to the second lecture. So yesterday we stopped just short of actually looking at some examples of BPS cohomology and looking at the proof of this main theorem that I call cohomological integrality, that relates cohomology of stacks that may be infinite dimensional to certain finite dimensional pieces, which is this BPS cohomology. So let us first, just to recap from yesterday, we had three classes of stacks we looked at. So first there were smooth stacks, then zero shifted and -1 shifted. So zero shifted are related, for example, to Higgs bundles on a curve, and -1 shifted to moduli of sheaves on a Calabi-Yau threefold. First, we start with the easier case of smooth stacks. So for simplicity, I'll be assuming that they depend on a reductive group G. So for example, we look at G bundles of degree 0, semi-stable G bundles of degree 0 on a curve. So what does this mean? In particular, stabilizers of all close points on our stack will be subgroups of a fixed reductive group G. So kind of a first example is a global quotient stack of an affine space by a group G, where the affine space is a self-dual representation of G. For example, the stack of representations of a symmetric quiver. One example is the adjoint representation and L copies of that, quotient by G. So if the group G is GLD, this stack is the stack of representations of the L loop quiver. Then, as I mentioned, the moduli of bundles or moduli of semi-stable G-Higgs bundles on a smooth projective curve C, semi-stable and twisted by a line bundle of degree larger than the degree of the canonical bundle on C. So this twist is needed to obtain a smooth stack.
But for usual, like G equal GLN,
Yes.
the degree of L for the usual Higgs bundle, it's exactly 2G minus 2, if I'm not mistaken. So which means that usual Higgs bundles are not included
in the first section. So they will be included in the third section.
Okay.
Yeah, so it's they will be included, but now we are discussing easier example. This is a setting from last time. So curly X is our stack with good moduli space straight X. So a standard example is we have a global quotient stack V mod G, and the good moduli space will be V double bar G, the affine quotient, which is the affine scheme with ring of functions, G invariant functions on the affine space V. Now we defined BPS cohomology, or I said that in most cases BPS cohomology is the first non-zero perverse cohomology of the projection of the IC sheaf on the stack. So here the stack is smooth, so the IC sheaf is just a shift of the constant sheaf. And what do I mean by in most cases? So for example, if X appears as a space of semi-stable objects, for example, semi-stable representations of a quiver, one needs an assumption that X stable is different from 0. So this is the BPS sheaf. This is how it was introduced. But in this situation where curly X is a smooth stack, the BPS sheaf is the IC sheaf on the good moduli space. So it is kind of a already studied object. But here the caveat is that the straight X, the good moduli space, is singular in general. So this IC sheaf is not the constant sheaf or not a sheaf of the constant sheaf. It's generally an IC sheaf. Okay, so let me mention a first version of this theorem that decomposes the cohomology of such a stack in finite dimensional pieces. So previous cases when the group was type A were also treated by Mozgovoi-Reinecke and Meinhardt. So here the cohomology of the stack XG decomposes in contributions coming from Levy groups. So there will be a finite dimensional piece, which is the BPS cohomology, in this case, intersection cohomology of spaces XL. So here XL is the good moduli space of the stack curly XL that one associates to a Levy group, times cohomology of classifying space of a certain torus. So the neutral component of the center of the Levy. And then we consider a relative invariance for the Levy. Now, this theorem, so these formulations are already standard in the literature in the case when G equals GLR. And there it is convenient to actually pack together these isomorphisms after all R's. So this is how one usually sees it in the literature. So one takes direct sum after cohomology of X GLR. Then on the right-hand side of the theorem, we have a sum after Levies. So the Levies will be product of GLRIs for a partition Ri of the of R. And the relative Weyl groups will be product of symmetric groups. So,
but you cannot mimic it for general G. So
yes, you cannot mimic. Yes, so for general G, sort of best case is just you stop at G. And you have one of this, it's the theorem stated.
okay.
Yes. Only for GLR, you can also do this summation. And so putting together the Levies, one actually can write them as a symmetric algebra on direct sum of intersection cohomology of the good moduli spaces times cohomology of BGM. So let's say that X is a stack of representation of L-loop quiver. So it is GLR, the adjoint representation GLR, L times quotient by the group GLR. So this is, this form was considered by Davis and Meinhardt. So this is an example of coha or quiver with potential, where the potential is 0. So this singular cohomology, so this coha, is isomorphic to symmetric algebra on intersection cohomology of the good moduli spaces, GLR plus L double bar GLR. So these are singular varieties in general. If L is greater than 1. And actually, their singularities, they might not admit nice resolution of singularities. For example, they might not have small resolutions of singularities.
Tudor, concerning this quiver with potential story, this intersection cohomology stuff, maybe it's in Davis and Meinhardt or something. But
Yes.
if you are interested in the existence of some graded space, not necessarily of geometric origin, which means like Poincaré-Bergov-Witz type, I
Yes.
believe it's already in our
Efimov.
paper
Ah.
with Maxim.
I see.
Yeah, because it's how
Ah.
this motivic BPS invariants can be defined. They can be defined using this isomorphism. Yeah, but without again, we did not study the relation to intersection cohomology, which is
Yes.
essential for you, but kind
Yes.
of
Yes.
the Poincaré-Bergov-Witz was already there. Yeah.
Yes. Yes.
Okay.
Yes. And then I think there's also work of Efimov, right?
Yeah, Efimov, but he proved, yeah, a bit implicitly, yeah, found a different proof. Yeah, okay.
Yes. 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 Yeah. Yeah. Thanks.
Can I ask a quick question on this isomorphism on
Yes.
the intersection on the right-hand side? That's the symmetric algebra of the direct sums with all the
Yes.
R.
Yes.
And the left-hand side that for each R, so that what does the direct sum on the left-hand side mean? And isomorphism is purely as a grid vector space, or because the right-hand side you don't have an algebra structure.
Yes. 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 So the isomorphism is as a graded vector space, and the grading is by well R, so it's just n. N, so this is R times Z, the cohomological grading.
Yeah, I mean, on the left-hand side, as you mentioned, that's coha.
Yes, and
You
actually,
do
so
have
this is
a different multiplication, but that's different from the right-hand side.
Yeah, so okay, that's very good. So it's let me just mention it's isomorphism of graded vector spaces, because this is the statement that we kind of consider, and the statement that will also be true for this quivers with potential and this analogous story. But in this case, the coha is super commutative. So I think up to maybe slightly changing the coha multiplication, this is an isomorphism of algebra.
Okay.
In this particular case of zero potential.
Thank you.
Yes, sure. Yeah, so, okay, so these are some examples. And maybe just to mention the example of these authors, Mozgovoi, Reinke, and Meinhardt. So they looked at cohomology of the stack of degree 0, semi-stable rank R vector bundles on a small projective curve. Of course, this is a classical problem, and the cohomologies of the full stack are known, and also cohomologies of these stacks of semi-stable, the stack of semi-stable bundles are related to cohomology of the full stack via Harden-Simon certification. And then so kind of one may consider that the left-hand side here, this cohomology of Bonn GLR0 semi-stable is known, and would like to compute the intersection cohomology. And this was a formula provided by them. So yeah, so how to define a map between the two sides? One uses parabolic induction for a general group G, or the whole product in type A. So these are some examples, and yeah, as I mentioned last time, my plan now is to actually explain the proof by focusing on one particular example. So it is the example of the L loop quiver. So this is yeah, not that straightforward. So sometimes there are some stacks for which it is straightforward to prove cohomological, or maybe not that straightforward, but it's not that hard. For example, if you have variation of GIT and you kind of and you are in such a situation in which you have a stability condition where there are no strictly semi-stable objects, and you understand well the spaces of semi-stable objects. But this doesn't happen for the L-loop quiver. So there are two possible linearizations, determinant and determinant inverse, but semi-stable objects, the open locus of semi-stable is the full affine space GL2 plus L. So we cannot play this game. And the standard technique, for example, used by Meinhard-Reinecke, was to kind of study the spaces using framed quivers. So our proof does not use framed quivers, so it also gives a new proof of this sort of more the standard version of cohomological integrality of Davison and Meinhard. But yeah, I'll be focusing on explaining how to construct this map star and how to show it's an isomorphism. And actually, all necessary ingredients appear in this proof. Yes. So first, we need to write our diagram of spaces that we'll be using. So an idea going back to Davis and Meinhard is to prove statements relative to a base to a good moduli space. So here, the base is this X2. So the reason will become apparent in the next section when we also impose a potential. So actually, the reason is that a local statement on X2 also implies immediately a statement where we have a non-zero potential, because vanishing cycles commutes with push forward along good moduli spaces map. So we have the stack X2. So the goal is to compute the push forward of IC on X2. Yeah, so this is the goal in star. This is what we want to compute. And we'll have a contribution coming from the IC sheaf of the base times cohomology of BGM. So the reason why this BGM appears is that the diagonal GM in GL2 acts trivially on the affine space, the adjoint representation plus L. So the preimage also over stable representations, over the stable points in straight X2 is BGM. So yeah, this cohomology will appear. And now why do we get the map from ICX2 into this push forward? This is non-trivial, and this uses kind of a weak form, let's say, of the BBDG decomposition theorem for the map pi. So this map.
So I'm a bit confused. Is this decomposition theorem for Artin stacks?
Yes, yes. So this is what it uses. Indeed. So it's not straightforward that there is a version of BBDG decomposition in this case, but there is. And actually, one uses frame type constructions to prove this BBDG decomposition theorem.
And who proved it?
So Kinjo.
Kinjo,
Yeah.
probably after Meinhard and
Yes, I
Reinecke,
think,
and maybe even after later than you. Yeah, all right. So, I mean, not in this particular case, but okay.
Yeah. So in this particular case, it's known. In this particular, sorry, that this push forward for the map pi satisfies BBDG. It's already in Davis and Meinhard, and it uses the explicit framed quiver construction of Meinhard-Reinecke. But Kinjo, it's kind of more general for maps, good moduli space maps.
Mm-hmm.
Yes. yeah, so this is kind of, okay, maybe I should make this disclaimer. So there are some frame constructions used in a place in the proof. Okay.
And here's a quick question on the top of the slide. Is that P? Yes. So
yes,
is that a proper and
yes, yeah, so this is proper.
See, so this is the one case. If we have different dimensions, that will be the parabolic. Replacing B will be the parabolic D
yes,
sub n.
yes,
Right. Okay.
yes.
Thank you.
And Q is smooth. Yeah. So okay, so this is this first kind of big contribution of the open locus in X2, and then we also have this other contribution coming from the addition map or via the whole product. So here, the second contribution comes from a decomposition of 2 as 1 plus 1. So it's a certain complex that will be supported over representations of the quiver that are direct sum of 2 representations of dimension 1. Okay, so this is star. And we want to show that star is an isomorphism. Okay, so how do we do this? It's a local statement on X2. So here I made a cartoon picture of X2. We have first an open locus of smooth points in X2. So it's this locus U, X2 minus the locus of polystable representations, the image of this addition map. So first we'll discuss this. Then the singular locus is also stratified. So first we'll have points in the image of addition map, direct sum of 2 representations that are not isomorphic. So we'll discuss this. And finally, we'll have most singular points, which is the diagonal inside x1 times x1. So we'll see that actually the case of points in image of alpha minus diagonal, locally, there we can find a small resolution of this space, singular space x2, because they have toric singularity. But in case 3, we cannot do that. Nevertheless, the proofs will be the same for 2 and 3 in our approach. Okay, so let's see. So we start with 1. So here it is straightforward. So over points in the open locus, the map from the stack to X2 is a GM germ. It's just this GM, the diagonal GM that acts trivially on the edge representation. So then star, this was star, will not have a second summon. This sim2 summon that's supported on addition image of the addition map is 0. So it's just, yeah, push forward of IC X2 restricted to U, and IC of U, which is just constant shift on U shifted dimension times cohomology of BGM. So this is indeed an isomorphism. Okay, so now we're looking at a singular point in image of alpha minus diagonal. So it's sum of 2-dimensional representations, and they are not isomorphic. So the neighborhood of this point is modeled using another quiver, which is this particular quiver. So it has 2 vertices and L arrows one way, L arrows the other way, and L minus 1 loops.
Can you comment on this? Why this is a model?
It's X computation. It's a so also this point that we're looking here, it's polystable, and locally on the good moduli stack for a polystable point that we write the sum of some stable with multiplicities. we can describe it. We can describe a neighborhood of this good moduli space map using a next quiver.
Okay, but this SSI, they are different, yeah?
Yes, the SIs are different, yes.
Okay.
So it's a version of Luna slice theorem.
Okay. Mm-hmm.
Yeah, so we get this simpler quiver. Yeah, so this is kind of a picture. So yeah, we had our initial map from the stack to the good moduli space. And now a neighbor near one of these points in the image of alpha minus the diagonal, we have this other model. It's the space of representations of the quiver. It has an affine space A to L minus 1. So this comes from the loops. But we'll discard this immediately because GM will act trivial in this space. So we can simplify our problem by removing this affine space. Yes, so okay, so this is what I wrote here. Also, as usual, the diagonal of GM will act trivial on the representation. So of course, we keep carrying this GM trivial stabilizer over all points, not only over the stable points. So the only kind of relevant stack that we'll have to consider is AL times AL quotient by GM, where GM is one of the two GMs there. So for example, the one corresponding to the leftmost vertex. So this GM will act on AL with coordinates with weight 1. And I think for simplicity, I also give a name to the coordinate. And with weight -1 on the second copy. So up to removing this affine space corresponding to the loops that was on which the group acted trivially, and also rigidifying by this GM chirp that acted trivially, we reduce the statement to star star. So now it is this stack is A to L quotient GM, with GM acts with weights 1 and -1. And we take its affine quotient. So we need to compute the push forward IC of this stack. Again, we'll have a contribution from IC of Y. So again, Y in general, it is singular. So it's a genuine IC sheaf. Yeah, so, okay, so this is just, so all these terms are analogous to the ones in star. And I also, the second term is the one coming from the extra sheaves that lie at the origin in Y, which is the only singular point, which is the point we chose in image of addition minus diagonal that we zoomed in and we took a slice. So we need to show that star star is an isomorphism. So the map star star is an isomorphism on the complement of the origin by case 1. These are points in the open U of stable points. So that's good. So now this is a main step is to consider the cone of this map. So we want to show, the goal is to show that the cone is trivial. But we know that the cone is supported over the origin. So now the trick is to reduce the problem to a simpler problem where the stack is just classifying stack. So instead of A to L mod GM, we just have point origin mod GM. And also to have such a reduction in which the cone can be detected. So what do I mean by this? We introduce artificially a function and take vanishing cycles for that function. And this function should have the property that it's Morse and actually has only one singular point, the origin. So why is this a good idea? Is because applying vanishing cycle for such a function will still detect the cone. But also applying vanishing cycle for this function will simplify this. We'll just make it push forward of vanishing cycle applied to ICY, but F is Morse. So it is just the critical locus, which is just BGM. Okay, so this is the idea. So we consider the function F, which is sum of xi, yi from I equals 1 to L. So I use notation and write F for both functions on the stack and on the good moduli space. So the critical locus is just origin mod GM. So so now I'm writing phi f minus 1. This is the function that preserves perverse sheaves. So the vanishing cycle shifted by minus 1. So so then star will be an isomorphism, that is the cone is 0 if and only if star is an isomorphism after applying vanishing cycle. Okay. So this is what we do. So here I rewrote the diagram. This is star. And now we apply vanishing cycles and the fact that vanishing cycles commute with push forward along good moduli space maps. So we need to compute the left-hand side. Yes, so here we already used the vanishing cycles commute with push forward. F has critical locus just origin. So this is just ICBGM. So BGM has dimension -1. So it is just the constant shift of BGM shifted by -1. Next, we need to compute vanishing cycle F applied to ICY. So here, a priori, this is not straightforward because we apply vanishing cycles, but not to the constant shift. And we actually apply vanishing cycles to the IC shift on a singular space. But remember that ICY here was actually the BPS cohomology. So it's the smallest perverse cohomology of the push forward along the good moduli space of IC of the stack, which is in this case, after we did this general rigidification, not the first cohomology, but the 0th cohomology. So this will be the 0th perverse cohomology. So after kind of commuting some of the functors, it will be the 0 perverse cohomology of push forward pi prime lower star of vanishing cycle applied to ICY. But this is exactly what we computed on the left-hand side. So it will be the 0 perverse cohomology of the push forward of ICBGM, which is QBGM shifted by -1. So this has 0 perverse cohomology. And then lastly, we have vanishing cycle applied to the contribution coming from the whole product, which was just constant shift at the origin times cohomology of BGM. But this is supported at the origin, which is in the critical locus, so it survives. But maybe here, maybe I made this mistake. So what color should I? Yeah, so here the computations were for this, not taking into account the push forward. So now we take the push forward, and the push forward of QBGM is just the constant shift at the origin, that's the cohomology of BGM. And on the right-hand side, we have 0 plus the constant shift -1 times the cohomology of BGM. So this means it's an isomorphism after applying vanishing cycle, so the cone was 0. So this is the trick, and it doesn't apply just in this situation, it applies more generally. So the idea is you kind of use this local description of the spaces of interest, and then so that you know the statement that you want to prove at all points except one particular point. And then you cook up a convenient Morse function that will localize kind of the problem onto that point. But as I said, the second case can be also treated using variation of JT. But the third case cannot, and this proof works perfectly well in the third case. So now we need to show it's an isomorphism for points in the diagonal. So for, yeah. And now there's no, we cannot simplify that much. I mean, the X quiver will be the same quiver in this case. We cannot do the trick we did before. But for simplicity, I kind of took the GM rigidification and I eliminated an affine space. So I went from GL2 to SL2 just for simplicity, just to have one singular point that we do. And now we consider, again, a quadratic function whose critical locus will be at the origin. And then, yeah, one plays the same argument. So again, after the simplification, we have the statement star will become a certain statement star double prime that I didn't spell it out. But as before, we'll know that it is an isomorphism everywhere by cases 1 and 2, everywhere except outside the origin. We take the cone that we know it's supported over the origin of the map from the right-hand side to the left-hand side. The critical locus of G is this origin, quotient in this case PGL2. So the map we want to show it's an isomorphism if and only if it is an isomorphism after applying vanishing cycles. So again, this reduces to two sheaves that are supported over the origin times some the origin that is the singular point O times some cohomologies. And the cohomologies on the left-hand side is B PGL2, and on the other side is B of the maximal torus and then Weil invariants, which is an isomorphism. Yeah, so this is the idea. Yeah, so here kind of just some comments that it is a well, yeah, it is general method, and it works for spaces as long as for the local model we can do the same trick. So if there exists a G invariant non-degenerate symmetric bilinear form on B, and this is indeed for many stacks of interest. Yeah, so in our paper, we not only considered, so we consider symmetric stacks, but we also assumed that they need to satisfy this condition on the tangent space that was satisfied in the most examples of interest. But the last month, this condition was eliminated by Enekar and Quijon.
So this quadratic form is used for this Morse to construct this Morse function.
Yes, yes.
Okay.
I don't understand the last slides, the right-hand side of, yeah, maybe move up. Yes, so the right-hand side of the cohomology ring of the classified space of GM. And what is this O2 acting?
This is the Weil group. So it's symmetric group on two
That's
elements.
a symmetric group of order 2. Okay, I see.
Yeah, yeah.
So the symmetric group acting on GM trivially, so.
No, it is X, so X maps to minus X. I hope I'm, yes. Yeah, I hope I'm not making a mistake, but this is QX, right? QH. And then the group X H maps to minus H.
Oh, I see. Okay. So that's the maximal torus. Yeah,
Yes.
thank you.
Yeah, sure. Yeah. So in particular, we also give a new proof of the Davis and Meinhardt theorem. But again, the feature is that it applies, for more general spaces. And also we allow more general groups in these arguments. So this was...
Tudor, before you go to this -1s and Calabi-Yau, 3 Calabi-Yau, you said that these BPS sheaves, they are not always, they do not always come from IC.
Yes.
And so when they do or when they don't, I mean, there is some abstract construction, by gluing, blah blah blah.
No, I think usually what happens is they are either 0, there is the trivial BPS sheaf, or they are IC sheaves. This is the dichotomy in this case. So
no.
they may be 0 when there are no strictly stable objects. So this also appears for quivers in this code.
Yeah, but this for examples, and I ask a general question: if you start with a good stack, whatever in your sense, then what?
Yeah. So yeah. So let me see if I have a person.
If you find with IC, so I will be fine as well. But since kind of a naive way of thinking is to construct a local potential and then look for sheaf of vanishing cycle and then glue them together. This kind of
No,
things.
but I think so. This is much simpler, and what I'm saying is that also for general smooth stacks, if you have this symmetricity assumption, the BPS sheaf will be either IC sheaf or it will be trivial. There are no vanishing cycles, and this is just a condition that can be phrased. So yeah, for quivers, it has to do with this stable, like the locus of stable. But then this can be also phrased in this language using the mapping stacks from GM into X or from A1 mod GM into your stack X.
All right. So you don't need, in your case, there is a local model, this quiver local model for -1 shifted where you are starting to discuss. Sometimes it also exists, I believe, due to Tudor whom.
Yes.
Yeah, all right. Okay, go ahead. Yeah.
Okay, so now we talk about -1 shifted symplectic stacks. So we consider our good moduli space. So here I wrote some examples. They can be G-local systems on a real compact oriented 3-manifold, or -1 shifted contingent stack of Higgs semistable, or the loop stack of Higgs semistable, or moduli of representations of quiver with potential. Actually, maybe I should say symmetric quiver with potential. Yes, so in this case, the BPS cohomology will be the first non-zero perverse cohomology of the push forward of this sheaf phi. Yes, so we assume we have a -1 shifted symplectic stack with orientation that allows us to glue the local models of vanishing cycle sheaf. And then this is our sheaf phi. Then we take the push forward and the first non-zero perverse cohomology. So it is not very explicit, and I think in general, even for quivers with potential, I guess even for triple quivers with potential, it is interesting to understand all summands of this perverse sheaf. So yeah, so this is there is a analogous version. So in the case of quivers with potential, it is due to Davison and Meinhardt. Yeah, so as I mentioned, of course, if you start with the kind of this theorem, if you start with this version of the theorem where you take singular cohomology, then all the space, like the space on the left-hand side is, for example, for quivers, it's some polynomial algebra. If you apply vanishing cycle, it will not be enough to detect the cohomology of vanishing cycle just from this space. But the idea of Davis and Meinhardt was, instead of proving this theorem directly as I wrote it, prove it local on X2 as some isomorphism analogous to star. Then if you have such a statement, you can either push forward to a point and then you get the previous theorem, or here you can introduce a vanishing cycle for a potential, trace of a potential, and obtain the statement for a quiver with potential. So we would like to do something similar. So kind of what I said, yeah, will amount to, yeah, well, ideally, what we'll have is that our stack mapping to the good moduli space has a local description on the good moduli space as a critical locus of a function on a smooth stack Y. Then we can use this Davis and Meinhardt strategy. So this, in this form, this is due to Park. But also, importantly, is to define a map from the right-hand side to the left-hand side. So in the smooth stack case, yeah, I just wrote it as an example for this L-loop quiver. So it has to do with parabolic induction, with kind of going through a stack of extensions. But in the global case, in the local case of symmetric or of quivers with potential, a map kind of yeah, the map that's used to define to go from right-hand side to left-hand side is appears in the paper of Kontevich and Soibelman. But it's yeah, a hard problem to define it for general -1 shifted symplectic stacks. So this was done by Kinjo Park and Safronov. So we're using their results. Okay, so this is kind of the ingredients appearing in this proof. Okay, so now zero shifted symplectic stacks. So actually the result for zero shifted symplectic stacks goes through -1 shifted symplectic stacks. Now let's consider, for example, the stack of semi-stable G Higgs bundles on a smooth projective curve, the usual Higgs bundles, not twisted anymore, or the moduli of G local systems on compact Riemann surfaces, or moduli of representation of a pre-projective algebra. So as we mentioned in the first talk, the BPS sheaf and BPS cohomology is defined indirectly in this case. So to our stack of interest XG, we associate this construction called -1 shifted cotangent stack. Then this falls under the previous section. So for this stack, we can define BPS cohomology, and then we use dimensional reduction to transfer it back to cohomology of X. So dimensional reduction is this isomorphism. So it goes between Borel-Moore homology of the stack X and cohomology of this sheaf phi, this gluing or vanishing cycle sheaf for the -1 shifted cotangent X. So let me kind of unravel what this is in a very particular example. So if we consider, maybe there are also more general statements called dimensional reduction, but one such statement will have this following easy example as a corollary. So if we take a polynomial in n variables and we look at the zero locus of this polynomial, this may be singular. Its Borel-Moore homology can be computed as isomorphic to a vanishing cycle cohomology of a function on an n+1 dimensional space. So we take our previous n-dimensional space and then time it with a1 with coordinate t, and we consider the function t times f. So I should be saying that maybe it's first time one learns this statements. I mean, the way they are introduced and the way they are maybe useful in this particular example that I gave is that we have vanishing cycle cohomology, which is has useful formal properties, as we already saw, but it's hard to actually compute in practice. So how do we do that? It's hard for a general potential, but in particular cases, it ends up being just some classical theory. So this is kind of the form of dimensional reduction of Kontsevic introduced in the paper of Kontsevic and Soibelman. So there are also other versions of dimensional reduction in terms of natural transformation of functors due to Davison. But the form discussed here is due to Kinjo. And kind of the way we're using it is not the way in this example. That is, we kind of know something already about this -1 shifted geometry, and then we move it to maybe the more classical geometry of zero shifted symplectic stacks. So this is one ingredient. And then we also need okay, so now we just get a sheaf, but it's on the good moduli space of t star -1x. Via some natural maps, for example, via a push forward. And this is where this ideas of factorization structures appear. This, what I mentioned last time, this kind of loop that we add by when we take this -1 shifted cotangent, that this has same eigenvalues. So this is called the support lemma. So we combine this, and then we also prove a version of our theorem for zero shifted symplectic stacks. Okay, so in the last 7 minutes, let me mention some application of BPS cohomology that I find interesting. So as I said, there are many developments, and I mean the study of this BPS cohomologies was motivated by problems in enumerative geometry of Calabi-Yau threefolds. So here is yet another such problem, a conjecture due to Toda. So if one considers a Calabi-Yau threefold Y, one can consider moduli space of sheaves supported on a curve beta, semi-stable with Euler characteristic chi and chi prime. And there should be an isomorphism between these BPS cohomologies. So this is already interesting, even if there are no strictly semi-stable sheaves, and one just uses the usual critical / DT cohomology. So, okay, so this is a Calabi-Yau 3 statement, but we can, so it's still, open in most cases. But one may try to see what it says when the Calabi-Yau threefold is a local surface or a local curve. Then we may use dimensional reduction and move to a statement involving some piece, in the Borel-Moore homology of a stack of semi-stable sheaves on the surface, that's more classical object. So let us say that instead of S being a smooth projective surface, we take also S in my presentation to be a local surface. That is, we consider a small projective curve and we consider the total space of rank 2 vector bundle over it, which is L plus L inverse time Kc. So if the degree of L is larger than the degree of the canonical on C, so we're in this L twisted Higgs case where it's a smooth stack, so it's just the BPS sheaf is the IC sheaf, then the chi-independence is proved. So there is this theorem of Maulik and Shen that intersection cohomology of L twisted semi-stable Higgs of rank R and degree chi is isomorphic to the same space where we change the degree to chi prime. Of course, these spaces are smooth if chi prime is co-prime to R, but they are not in general. And how does one prove such a theorem? One considers the map to the Hitchin base from the space of Higgs bundles to this large affine space, and so the Hitchin base parameterizes spectral curves, and over the open locus of smooth spectral curves, the preimage of the Hitchin map, the fibers of the Hitchin map are Jacobians over smooth curves. Over
I'm
the smooth
confused.
curves.
Your L has a degree bigger than degree
Yes.
of, so it should be some kind of a L twisted version. It's
Yes.
not really. Are they Jacobians or are they twisted Jacobian?
No, they are still Jacobians.
They're still. Yeah. Okay.
Yeah,
Yeah.
there is still
probably.
a spectral correspondence, so we still can. Yeah.
Yeah. Okay.
Yeah. Yes. But I mean, it's not. Yeah. Okay. Yeah, I'm not sure what to say. Yeah, they are still Jacobians. And then yeah, over this large open locus, one knows what the fibers are. They are Jacobians of this smooth spectral curves. So one knows how to compute the push forward over the locus of smooth spectral curves. And then the theorem, kind of using this goal support lemma, is that the supports appearing in the BBDG decomposition for this push forward are full. You don't have supports corresponding to singular spectral curves. So then the statement follows just from the fact that cohomology of peak on the smooth spectral curves does not depend on degree of light. Okay, I have 1 minute left. So yeah, maybe I'll stop at this Maulik-Shen result, and then I'll just take maybe a couple of minutes tomorrow to discuss this what it says for usual Higgs bundles. For usual Higgs bundles, we don't have a nice description of the supports in this push forward of the map to the Hitchin base. We don't know the supports actually, but we know that in general there will be supports over the singular spectral curves. But nevertheless, there is a theorem of Kinjo-Koseki that proves chi-independence in this case. Yes, so then I'll also make some comments.
Yeah, tomorrow because it's interesting stuff.
Yes.
And also, since we return to Higgs bundles tomorrow, I understand that people kind of like Higgs bundles, but for example, if we have the following setup, we start with a complex surface, remove zeros of the this remove the whatever anti-canonical divisor, yeah. So what we get is a Calabi-Yau open Calabi-Yau surface, and then we look for a stack of coherent sheaves on this Calabi-Yau with one-dimensional support. Yeah, for the cotangent, it's exactly Higgs, pure one-dimensional support, and with something a bit not clear, with a good behavior and the anti-canonical divisor. The word good should be specified. And so I ask the same question.
So you want the moduli space on the smooth projective
yeah,
curve
more
that
something more general.
intersect.
For example, let me give you an example. Take C star square. It's a symplectic surface, endo it with a standard symplectic form, and compactify it to a toric surface any way you like. Choose any toric and then you look for coherent sheaves on C star square with one-dimensional support, and for example, such that it's this support intersect toric divisors transversally, whatever, and finitely many points which you fix. And so it should be a zero zero shifted symplectic stack, because it's kind of two Calabi-Yau. It's analogous to Higgs bundles, where you fix with regular singularities when you fix eigenvalue, something like that. So everything should be, I mean, the results should be the same, but I am curious whether anyone considered this setup.
Yeah, I guess maybe the first thing would be to have a kind of clear construction, right, of the moduli space.
Yeah, you still have, you see, if you have a spectral curve, you can consider pure one-dimension sheaves, which are just line bundles on this curve, and this is, yeah, which give you this tori, which you mentioned as a fibers of the projection on the Hitchin wave. And Hitchin base is moduli space of supports these curves.
Yeah,
but it's exactly. So then everything looks kind of very similar, but you cannot just apply everything which you have in your disposal in the case. So,
it's a good question. Yeah, I mean, as far as I know, no one considered this.
Yeah. Okay, all right. So we'll continue then tomorrow, yeah?
Yes, I have just one slide about
yeah, that's
this.
okay, but this is important slide, so I don't want to do it fast.
No, I was just saying, yeah, for tomorrow, it's just one more slide about this, and then it's categories.
All right. Okay, thank you very much, and then see you tomorrow.
Okay,
Bye.
bye.